In this video, we're going to cover the distribution of the sample proportion. And let's recall what a proportion is. So a proportion is just the decimal form of a percentage. And so is what this tells us then is that the proportion for anything is going to be between 0 and 1. Just like if we were talking about percentages, it would be between 0 and 100. And we do have notation here that distinguishes the parameter or the population proportion from the statistic or the sample proportion here. So we'll use p hat for the sample proportion and just p for the population proportion. All right. And there's one more thing to note up here is that we're going to be working with categorical data now. We've been working with not only quantitative data, but it's been continuous. When we were talking about the distribution of the sample mean and when we were performing those hypothesis tests and confidence intervals. But now, yeah, we're going to have categorical data. And it's usually going to be of the form of yes or no, fail or pass. Kind of these binary situations. Has somebody healed after their surgery or not? Okay, things like that. And that's how we're going to end up with these percentages is we'll be looking at, maybe what fraction of people were healed. Okay. So let's move down here. And so we have the sampling distribution of a proportion. So even though we're going to be working with categorical data, it's going to end up that we can very well approximate the distribution using the normal distribution. Okay, and so what actually describes the categorical things that I was talking about up here that fall into, again, like pass, fail, they got better or they didn't, that kind of situation. That's actually called the binomial distribution, and it's a discrete distribution. And so it's actually really interesting here that we're going to be able to approximate it using a continuous distribution. And if I get a chance to here later today, I'll try to put together a little a visual for this so that you all can kind of see it maybe tomorrow in class. All right. Now, here's the deal is we are going to be looking at how the sample proportion is distributed, just like how we were looking at how the sample mean was distributed. Okay. And if you want to think about how one of these sampling distributions might get formed, is maybe I could send out everyone from the class, okay, and they could do some sort of survey where the answer is maybe yes or no. And when you all are done, you all report back to me a sample proportion. And let's just say it's the proportion of people that said yes to that question. Okay. And so I would start forming a histogram based around these proportions that are given back to me. And if I kept sending students out to perform this survey and keep collecting these sample proportions, that histogram is going to start to look normally distributed if we satisfy some certain conditions that we'll talk about here in a second. Okay. So for one, this normal distribution that we're talking about here, it's going to be centered at P. In other words, and let me write this here. So this means that the sampling distribution for sample proportions is just equal to the population proportion. All this is really saying is that if we were to flip a coin 10 times and repeat that experiment over and over, that on average, we'd wind up with about half heads, half tails. That's all that's really saying there. Yeah. Now, next we have the standard deviation for the sampling distribution. And so the notation for this, we sometimes will write sigma sub p hat. And then we have that little formula there. I'm going to write it in a very slightly different format. There we go. All right. So yeah, this is really interesting that we're going to be able to do this here. Okay. Now, but let's see what the kind of restriction is that we have. So we need the sample size to be large enough that when we do n times p, that number needs to be greater than or equal to 10. But we also need n times 1 minus p to be greater than or equal to 10. Okay. Now, this right here really actually means the number of successes, because you can see up, I want to be a little bit careful about how I word this. Maybe I won't say exactly successes, but the n here is the number of people. P is the proportion of successes. So this would be the number of successes that would be expected in a sample, is what I would say. And this over here would be what we would expect for the number of failures. So, right, we have 1 minus p here. So that's the probability of a failure. And then times n, which is the size of the sample. And so we would expect essentially on average that this is how many failures we would get if we were working with a sample of size n. Okay. Now, so that's what we need in order to assume that the sampling distribution is normal. If we don't know that the sampling distribution is normal, we don't know if any of the probabilities we compute are accurate. So it is technically an important part there. All right, well, let's go ahead here and give a couple problems a try. And is what we'll eventually do is we'll get into hypothesis tests and eventually confidence intervals. Okay, here we go. So this is according to the CDC, the proportion of all gonorrhea cases tested in 2014 that were resistant to a major antibiotic was 0.38. A researcher plans to take a simple random sample of 100 medical records of patients diagnosed with gonorrhea in 2014 and obtain the proportion that showed resistance to a major antibiotic. What is the probability that 40% or more cases from the sample are resistant to a major antibiotic? So we have a few things to write down here. First of all, let's think about maybe what this number here is. So this says all, right? They're talking about a population proportion here. So I'm going to go ahead and write that in. P is 0.38. And you might remember, if we are actually answering a question about a sampling distribution, as we wrote up here, the mean of that sampling distribution should just be the population proportion. So this normal distribution that I'm going to have over here, I know it's going to be centered at 0.38. There we go. Let's see what else we have. We have our random sample had 100 people in it, or medical records. There we go. And what else do we have here? I think that's about it. Okay. So we also can find something that we're missing here, which is the standard deviation, right? It doesn't feel like we've been given enough information here, but we have. It's just we need to use this formula here for the standard deviation of the sampling distribution. So I might do that right here. All right, and so again, P is 0.38. And then we want 1 minus P. And then we want to divide this all by N. There we go. And so I would like to actually write that where I have this question mark, but I think just for the fact that that's barely going to fit there, I just might write sigma sub P hat. All right, let me see if I can make myself a little bit more room here. I think I can. There we go. All right, and so we have one more thing to do. We have this probability that we are trying to find. It says, what is the probability that 40% or more cases from the sample are resistant to a major antibiotic? Okay. So remember, we need this written actually as a proportion. So that would be 0.4. And so that would be over here, somewhere to the right of 0.38. And we want to know the probability again that we would have this proportion or higher. So to find that, we will just use normal CDF. Our lower bound is 0.4. Our upper bound is E99. We have the mean of our sampling distribution is 0.38. And then our standard deviation is that big messy thing there. And so we just need to get this into our calculator and we can find this probability. And I will type in that standard deviation just like that into my calculator. There is no need to find the decimal approximation for that standard deviation unless you're asked for it. Okay. So I'm going to go ahead here and hit second in VARS and then number 2 for normal CDF. And then let's start typing in our lower and upper bound. There we go. And then we have 0.38 here. And then our standard deviation. So I'm going to type in the square root 0.38 times 1 minus 0.38. And let me scoot this over. And then I want to divide that by 100. And hit paste. There we go. So we're getting about 0.34. All right. So is what this tells us is there's about a 34% chance that in this sample of 100, that 40% or more of the cases would be resistant to a major antibiotic. All right, so let's scoot down and give another one a try. Okay. This one will probably be a little bit easier to interpret. But I do want to point out up here, right, we were talking about whether whether or not there was a, let's see here. Let me make sure I'm using the correct words here. Okay. So yeah, we wanted to know um, what proportion of gonorrhea cases were resistant to a major antibiotic. Okay. And so they were either resistant to a major antibiotic or they were not. Okay. Again, that binary that I was talking about before. And here the binary is whether somebody lives in the Northeast or not. Okay. And so this says of the population of the United States, 20% live in the Northeast. So that is our population proportion. Let's just go ahead and record that. And right, since I know that that's my population proportion, I'm just going to go ahead and put 0.2 here. And I could actually start and compute my standard deviation, right? It should be 0.2 times 1 minus 0.2. And we know what 1 minus 0.2 is. That's just 0.8. So I'm just going to write 0.8 here. Let me see if I can write that with a little bit smaller marker here so that it's easier to read. Okay, so there's P times 1 minus P. And then I want to divide that by the sample size, which is 200. And then let me close that off. There we go. Okay. Yeah, so if 200 residents of the United States are selected at random, find the probability that at least 50 live in the Northeast. So at least 50. Okay. So the problem here is they didn't give us the proportion that would go along with at least 50. Well, let's think about what that sample proportion would look like, maybe if it was exactly 50. Well, if it was exactly 50, then p hat here, our sample proportion, would be 50 out of 200. Okay. So 50 out of 200 is actually 0.25. So no, 0.25 is somewhere over here to the right of 0.2. And so again, we want to know the probability that at least 50 live in the Northeast. So that's going to give us a sample proportion of 0.25 or larger. And let me check that this last one also was a case where we wanted to look at the upper end. Yeah, okay. So yeah, both of these examples here, we're looking at the right tail. There we go. And so next, I just need to use normal CDF. We have everything we need here. So we have our lower bound, which is 0.25, our upper bound, which is E99. The mean of our sampling distribution is 0.2, and the standard deviation is 0.2 times 0.8 over 200, and then we just need to square root that. There we go. And so let's get this into the calculator. All right, so we want second and vars. Number 2 for normal CDF. We want to type in that lower bound, the upper bound, the population proportion, or in other words, the mean of the sampling distribution. And then here, we need the standard deviation for the sampling distribution. And there we go. And if I scoot this over, we can see we're getting about 0.04. All right. So with this large sample, it would be pretty unlikely to end up with 25% or more of the people being from the Northeast. All right. So let's take a look at performing our hypothesis tests here. Okay. So now, when we perform our hypothesis tests, um, we are going to have a population proportion and a sample proportion as opposed to a population mean and a sample mean. So if we were to maybe write in here what this should look like is all of these are going to be centered at P naught. This is the number that is equal to the population proportion. And actually, to be a little less confusing, I think I'm just going to write P. So I could really use either one here. Okay, so this is the normal distribution that we would be looking at. And I think I want to put this on all three pictures here real quickly. Let me see if I can just real quickly copy this. There we go. All right, so in the first picture here, our alternative hypothesis is that P is actually bigger than was stated in the null hypothesis. So if that happens, the hope is that our sample proportion lands us somewhere over here to the right. Okay. And I think I'm going to try to shrink this up a little bit more so that I can write in P hat there. There we go. I think I got enough room now. Right. And if P hat was actually smaller than P, then it wouldn't support our claim at all. And there wouldn't really be a point in performing the hypothesis test. So this would be case one. Okay. P hat, on the other hand, could land, let me rephrase this. In our second case, we think that the proportion is actually smaller than was stated in the null hypothesis, and hopefully our sample then lands us somewhere off to the left of P, and that would look something like this. And then lastly, we have our two-sided or two-tailed case where we just think that the proportion might be different than what was stated in the null hypothesis. And so P hat could land on either side. We don't know which of the two sides it's going to land on. So once it does land on a side, we'll shade the tail on that side. And then we're going to go shade the equivalent side on the other side. The equivalent area on the other side. There we go. All right. And so to find these p-values, we're just going to use normal CDF for all of these. Okay. Maybe I'll write in how we would find maybe this one. Okay. But I think you'll get the idea after this one. Plus finding the p-value. And by the way, this is a little bit confusing now. We're going to have a p-value. We're also going to have P for the population proportion and P hat for the sample proportion. So there's three P's here now. But we have normal CDF. In this case, there is a lower bound. It's p hat. There is no upper bound, so I'll use E99. And then we'll have our mean of the sampling distribution, which is equal to the population proportion P. And then lastly, to get the standard deviation, we need that formula, which is P, or the square root of P times 1 minus P divided by N. There we go. So that's what that'll look like. And we're going to go and we're going to do 2 examples to make sure we have this down here. Okay. Now, there are requirements for this process here, and you can see that this is really stating the same thing that we saw up above for the sampling distribution. We want n times p and n times 1 minus p to be 10 or more. Okay. And when we fail and reject, or maybe I should say, when we reject the null and when we fail to reject the null, that's going to work actually in the same way as it did previously. Okay. So let's do an example. Okay. So this is the standard treatment for a disease works in 0.675 of all patients. So you can see here, especially with that word all, that they are describing a population proportion here. So I'm going to write in P equals 0.675. And in fact, if I want to now, that means I could actually write what distribution we're going to be working with. And I think I'm going to write a little bit smaller because P here is got 4 numbers I have to write down for it. So we have 0.675, and then the standard deviation here be the square root of P times 1 minus P. And then we need to divide that by the sample size here. And we haven't made it that far, but you might already be able to see it. It is right here. It's going to be 100. Okay, there we go. So a new treatment is proposed. And the question is this new treatment better? Okay. And we do need to test this. Okay. And so to test it, we're going to take a sample of 100 patients. And is what happened is 77% of these patients were cured from this disease. Okay. So is what that would be is that would be P hat. So let's write in P hat. That is again our sample proportion. And it's not just the 77, right? This needs to be like a number between 0 and 1. So it should look like a fraction or a decimal. Okay. So this, I could write it as 77 out of 100. Or if I wanted to, I could write it as 0.77. Okay. Either one is perfectly fine. All right. So this sample proportion is actually bigger. Okay. So that puts P hat over here. And I'm going to just write in the number here for P hat. It's 0.77. Okay. Now, I actually have skipped a couple steps here. Let's jump back here for a second, and we're going to write in our null and our alternative hypothesis. Okay. So when we write our null, remember it used to be the population mean that we would write here. But now you're going to write the population proportion, which is just P. And just like before, the null should always be P equals some number. And the alternative will be P is greater than, less than, or not equal to that same number. Okay. And so we already have the null here. It's 0.675. Okay. And so if we want to know if this new treatment or, new treatment is better, then we want to know, is P bigger than 0.675. Okay. There we go. And so now we can go ahead and we can use our normal CDF and we can find the p-value. Okay. Let's do that. So we're going to have normal CDF here. Our lower bound is that 0.77. Our upper bound is E99. The mean we've already written is 0.675. And the standard deviation for our sampling distribution is going to take up a little space here. And then let's type this into the calculator and we will have the p-value. And so, right, we want second and vars, and then number 2. And so then our lower bound, our upper bound, and on to the standard deviation. And what was our sample size again? It was 100. All right, and let me just make sure that this all looks good here. All right, let's go ahead and paste. And so we're getting about a 0.02. Let's go record that. And is what you might note here is we have our level of significance right here. So it's 0.01. And so we just need to decide whether the p-value or the significance level is larger. And so we know that 0.02 is bigger than 0.01. So this means that our p-value is right bigger than the significance level. And when that occurs, we fail to reject the null. All right. And so is what this also tells us then, if we fail to reject the null, is that we don't have evidence for the alternative. So we don't have evidence that the new treatment is any better than the old treatment. And if we were to mention anything about statistical significance here, we would say that our results are not statistically significant. We did not change the status quo here. Okay. All right. Well, let's go ahead and we'll move on to the next hypothesis test here. Okay. So, sleep apnea is a condition in which the sufferers stop breathing momentarily while they are asleep. Okay. The condition results in lack of sleep and extreme fatigue during walking or waking hours. Okay. And so we're going to end up looking at the population of truck drivers because they're a group that we would like to be getting a full night's sleep because it's dangerous to drive when you're sleepy. Okay. And so, is what we're being told here is that a current estimate is that 18 million out of the 312.7 million Americans suffer from sleep apnea. Okay. And they have nicely given us what percentage of the population that is that suffers from sleep apnea. Okay. Now, That is our population percentage, but we need a population proportion, which would just be P equals 0.058. I just need to write that 5.8% in its decimal form there. Okay. So there's that. Let's maybe also go ahead and compute the standard deviation because we're going to need that. Okay. So over here, again, I'll just write a little bit smaller. So that's where it's going to be centered, is at that 0.058. Then I need to take that 0.058 and multiply it by 1 minus 0.058, and then divide by the sample size, which we haven't actually read that far, so maybe I'll leave it like that. Yeah. All right. But I also want to note, because we did have the sample, or sorry, not sample, population proportion already, we already know that that's going to be what goes in the null hypothesis, right? Before it was the population mean, now it's going to be the population proportion. So I'm going to write that in here like this. And do note that means, even though I haven't read the rest of this question, I can start to write down my alternative as well. The question is just what's going to go right here. And we'll figure that out after we read a little further. So it says, a safety commission is concerned about the percentage of commercial truck drivers who suffer from sleep apnea. They do not have any reason to believe that it would be higher or lower than the population's percentage. Okay. So that right there, to me, is an indicator that this is going to be two-tailed. Okay. There is no indication on whether they think more truck drivers are going to have sleep apnea or less. Okay. So I'm going to put not equal to here. So to test the claim that the percentage of commercial truck drivers who suffer from sleep apnea is not 5.8%, a simple random sample of 350 truck drivers. So that is our sample size right there. I'm going to write in the 350. The random sample of 350 commercial truck drivers is examined by a medical expert who concludes that 30 of them suffer from sleep apnea. So that right there is P hat. Okay. And remember, P hat should be a fraction or a decimal number between 0 and 1. Now, that fraction should also be a number between 0 and 1. It may not be obvious what decimal number it's equivalent to. So here we have our 30 out of 350. Okay. Let's get an idea of the decimal approximation for 30 over 350. Let me make sure that's right. Yeah, 30 over 350. Okay. So yeah, we're getting about 0.086, let's say. There we go. So on this picture here, that's going to be off to the right. There we go. Now, we didn't know we were going to land, or we didn't suspect that we would land over here on the right. Okay. So is what we want to do is also shade the other side. Okay. So we're not going to find the probability that we would get a sample proportion this large or larger. We're going to find what is the probability that we would get a sample proportion this far from the mean on in either direction. Okay. Just what is the probability that we would get a sample proportion this extreme? Here we go. So the easiest thing to mess up on here is to forget to multiply by 2. So maybe in my calculator right now, maybe I'll just put 2 times, and I'll hit second in vars and hit number 2 for normal CDF. Yeah. And let's go and start writing in some of this stuff that we need here for a p-value. And then we can go plug all that stuff into the calculator. So our lower bound here is 0. I'm just looking at this one where we already know what one of the bounds is here. So I'm going to write in that lower bound, and then my upper bound, and then the mean. And then the last thing we need is that standard deviation. So I'm going to maybe make myself a little more room. There we go. Okay. So we need to get this all typed into the calculator. So I'm going to pull mine up here. Now I wrote in 0.086 here for p hat. That is not the exact value for p hat. I'm going to change that to 30 over 350. I don't want to lose any accuracy if I don't need to. All right. So going back in here, I'm going to shrink this up a little bit so that we can see some of our work here. So we had the 30 over 350, E99 for the upper bound, and then a 0.058 here. And I'm going to just come down here and just type over some of this stuff, since this is pretty much almost exactly what I need. So yeah, we have p times 1 minus p, and then the sample size again was 350. So I'll just type over the 100 here and put in my 350. And I'll hit paste. And if I were to scroll over here, you can see I have my 2 times there. So I'm getting about, I would say about 0.027. Okay. Yeah. So now this is the p-value. And so is what this means is there's only about a 2.7% chance that we would end up with a sample proportion this extreme in either direction. Okay. Now, we do have a significance level that we need to compare this to. So our significance level is 0.01. Okay. So this is bigger again. So that means that we're going to fail to reject the null hypothesis. And so is what this means is that we do not have evidence for the alternative. And the alternative was that the proportion of truck drivers that suffer from sleep apnea is different from the rest of the population. Okay. And lastly, this also means that our results are not statistically significant. There we go. All right. So there's one more thing that we need to talk about, and that is confidence intervals. So we have a couple things to say about them. So, for one, of course, we have a formula that we're going to want to talk about, but also we need the sample size to be large enough again. Okay? And you can see highlighted down here that we only want to use this if the number of successes and failures in the sample are at least 15. All right. And so we'll take a look at that when we maybe do our next example here. Okay. So before we actually try to use this formula here, I want you to note that this is actually in the exact same form as our previous formula. So before we had x bar plus or minus z star times sigma over the square root of n. Okay. Well, this was the sample mean. This is the sample proportion. Okay. Z star, this is the number of standard deviations that we want to go to the left and to the right so that we can capture a certain percentage of the data. If we were actually centered on the if we were actually centered on the population proportion. Okay. So that's a lot to say there. But Z star is just the number of standard deviations we want to go left and right. Let's leave it at that. Okay. And then this part here and this part here, these are both the standard deviation for the sampling distribution. It's just the one on the right is the one that we use for means, and the one on the left is the one that we use for proportions. Okay. Now that you see that these have really the same form, um, the only other thing I want to note is that we're using p hat here instead of p. Okay. If we scroll up in our notes here and we look at our standard deviation formula for the sampling distribution, okay, we can see that p is actually there, not p hat. Okay. And so there's a reason for this. And that is when we actually create a confidence interval, the goal is to capture the parameter. Okay. So before, the goal was to capture the population mean. So now it's going to be to capture the population proportion. So what this means is we don't know the population proportion P here. And so we're using P hat as a stand-in for P here. So let's go ahead and do an example here. So it says, for a class project, a political science student at a large university wants to estimate the percentage of students who are registered voters. He surveys 500 students and finds that 300 are registered voters. Compute a 90% confidence interval for the true percent of students who are registered voters and interpret the confidence interval. So let's see exactly what we have here. So we have that our sample size is 500. We also have that 300 are registered voters out of the 500. So we can form p hat here, the sample proportion. And if we were to write that in decimal form, that's 0.6. Okay. And lastly, the only other thing we need is z star. Okay. And so we have 90% confidence here. And so if we come up to our table, we see that z star should be 1.645. Right. And then let me remind you of what our formula is going to look like here, and we'll plug all these things in. So we have p hat, and let me use a little bit bigger marker here. So we have p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. Right. So is what this means for us is that we're going to have this 0.6 plus or minus 1.645 times the square root, and then we should have p hat, which is 0.6, and then 1 minus p hat then would be 0.4, and then we want to divide that by n, which is 500. And so let's get this into the calculator. All right, so we have 0.6. I'm going to do the lower bound here first. So I'm going to write minus 1.645, and then the square root of 0.6 times 0.4, and then we want to divide that by 500. There we go. And if we want to get the upper bound really fast, we can just hit second and enter here. And then we can just arrow over and change that subtraction to addition. There we go. We have our upper and lower bound. I'm going to copy those over. So if we were to write in our confidence interval, we can write this in multiple ways. I'm just going to write it in interval notation here. So if we round each one of these to 2 decimal places here, I'm going to have 0.56 for my lower bound and 0.64 for my upper bound. And I do think in this question that they did ask for the percentage instead of the decimal form here, our proportion. So maybe let's add this in as a percentage as well. So if we were to do that, that would be 56% to 64%. All right, and so is what this means, right, is 90% of confidence intervals formed using this process for samples of size 500 will come back, or will contain the true or population percentage of people that are registered voters, or students that are registered voters. Okay. Or the short way of saying this is that we are 90% confident that the true percentage of registered voters is between 56% and 64%. Okay. But again, we may have one of the lucky 90% of confidence intervals where this is true, but we may have one of the unlucky 10% where this is not true. Right. And so that there wraps up the distribution of the sample proportion.